Hey everyone, welcome back to the shop, and today we're going to get started on the last major machining op for the USA made hardtail vise, and that is this nut right here. This is the hardtail nut that fits inside of the hardtail casting here that bolts onto the back of the vise. So this is the original that's got the metric thread inside there, and then this of course is the nut that we made in a previous video. The threads in there are 1.25 inches 5 to match the new spindle that we machine. So what we want to do is modify both these pieces so that the hardtail nut and this new nut will fit together. My plan of attack for doing this is a male-female thread, male-female fit. So one piece, probably this one right here, is going to have your male threads on it. So we'll turn it down, thread it. I haven't exactly figured out what thread size, but I'm leaning towards probably about 1.5 inches 12. It's probably what we're going to go after. I just need to do some measuring. Basically what I'm wanting to do is split the difference between the inside, which is 1.25 inches, all right, and this OD, which is 2 inches right there. Because once we put this together, this nut is going to be turned down to match the rest of that 2 inch to fit inside this 2 inch bore right here, okay? So probably around 1.5 inches 12 thread is what we're going to machine on that. I made the nut 3 inches long, and that is to match the thread length that's inside the original casting right here. That's about 3 inches. So if you take your trusty steer it hook rule, stick it in there, you can catch the back thread there, and it's right at 3 inches long, just a shade over 3 inches. So since there's a lot of extra material right here, once you get past that thread, it opens up and it just turns into more of like a tube on the inside there. Since you got about 3 inches of thread and you got a little thickness here, what we'll do is probably just part this off by 2 inches long. Just part it off, and that's going to give us about 1 inch of these threads here that we can use to thread. So what we'll do is just finish boring these out so that we know 1.25 inches, the spindle will pass through there without rubbing it. And then we can go ahead and thread this piece with a female thread to match the threads that we machine on this here. And then those two will screw together. We'll screw them together tight, maybe use a little Loctite on there. And then what I was thinking, I got a couple of options. I really haven't decided which one I want to use, but we do have a tapered pin here, and I got a couple tapered reamers. This is some of my dad's tooling. We've also got some spring tension pins here. Now this would be another good option too. And basically, once it's all together, you set it up in the mill and drill a hole that splits the wall thickness there so you don't get into the threads. Just drill a hole in there and then just drive one of these pins. If we use the tension pin, just drive that in there, and then we'll have to make sure that the length of it is not sticking up above the 2 inch diameter, so it'll slide through that hole. And then this just gives it some extra insurance that these two pieces are not going to unscrew. Once you have some kind of pin in there, it's not going to come back apart. So a spring tension pin would be the simplest way to do that. A tapered pin is a little bit more elegant, a little bit more of a style that a lot of the old machine builders used to fasten pieces together that they did not want to come apart or not move. And with a tapered pin, you can easily drive that in there, like so, drive it in there tight, and then set this back up in a lathe and turn both ends of the pin off so that it just matches the OD of the nut there. So again, we may just figure this out along the way. What I want to do is go ahead and get this set up and get started on these pieces and at least get these two threaded together. And I think by that point, we might figure out what kind of pin we're going to use to fasten them together. So we'll go over to our Precision Matthews lathe to get this job done. We're going to set a steady rest up so we can get in here and part this off, do all our ID threading on that. But I think what we'll do first is go ahead and get this one turned and threaded so that I can use this piece as a gauge when we're cutting the ID threads here. We'll have this already together so we can thread this and make sure they screw together nicely. This is just a more convenient piece to use as a gauge versus this long nut right here. So that's my thinking on something like that. That's what I've done many times. Get this piece threaded, do your ID threads, that way you can fit them easily on the lathe. All right, so I'll meet you over at the Precision Matthews lathe and we'll get started on this. I realized that I made a mistake in the previous video when we were talking about splitting the difference between 1 1/4 and this 2-inch diameter right here, and I said we would just make an 1 1/2 inches. If we want to properly split the difference between 1 1/4 and 2 inch on the OD there, we need to make it 1 5/8. So that's the diameter that we're gonna go with. So there's about 1 5/8 on the calipers. So we'll turn this down to 1 5/8. We're gonna turn it down 1 inch back, and we'll machine a 12 pitch thread on there, and that'll be in between the size. So once we bore this out, we'll bore this to the tap size for 1 5/8 12, and then fit those two together. So I just wanted to update you guys on that. That's the diameter we're going to shoot for, is 1 5/8 12 for this male thread. We're going to use our 3-jaw chuck here to turn and thread this nut. And it's possible we may swap this out for the 4-jaw when we go to do the hardtail nut. The flange on it, it actually is turned, so we'll just have to set it up and see. I just want to make sure this is running nice and true. So as long as this journal and this journal is turned concentric, we should be able to put that in the 3-jaw there and run it in the steady rest. Let's get our 0 set right here. So I'm going to bring the tool up and just very gently bring it up until I feel it just touch that face and stop moving. All right. So now up here on the DRO, we're going to take and we're going to set a 0, but we know we're on the face. I want to take it 1 inch back. I give myself 10 thousandths to clean the face up at the shoulder there. So we'll do on the Z, -0.9990, enter. All right. And then now if we go ahead and move our tool back, and we come down here, you can hear it beeping. All right, so there's our 0, -4/10. All right, so this works, and a lot of us do this, but what I would rather do is not pick my eyes up here and look at the DRO. What I would rather do is keep my eyes focused down here on the cut. What I'm looking at the tool, I'm looking at the workpiece. And so since you're looking down this way, it's easier to look down here at a dial indicator to see your 0 approach. So I like using this. I have a lot of guys ask this. So this is the mag back indicator designed for a lathe, made by Edge Technology Products. You guys can buy this from KBC Tools. They're not that expensive, and it's a very handy tool to have. The back of it, they've got plastic on here so it does not scratch and wear the ways on your lathe. You got a couple magnets in there, and this fence here is designed to be parallel with the plunger of the indicator. All right, this works really well. So we're going to stick that back on there, and I'm going to bring this up. Now, since the needle actually starts about the 10 o'clock position, 12 is the natural 0 that you like to look at, but I like a little bit of run out room as we approach. So I'm going to bring this on around. Just kind of, those magnets work good, but I'm trying to get it to where the needle is at the 6 o'clock position. So right about there. And we'll rotate that 0 on around to line up with that dial indicator. Now when we're coming up to our shoulder, I'm watching this needle come around to the 0, and it should match up with our 0 on the DRO. So we come back, we're cutting, we're cutting, we're cutting. It's going to come up and it's going to come around here to that 0 right there. And you can hear the DRO screaming at me, the 0 approach. And you can turn that off, by the way, if you don't want to hear that beeping. You can just disengage it. So anyway, I just wanted to show that, and why I like using a dial indicator on the lathe is because I'm keeping my eyes focused in this direction, and it's easy to see this and keep up with the tool versus lifting up and looking at the DRO. All right, the OD of our nut I think is around 2 1/4. Yep, 2 1/4 OD. So let's take that down to 5/8. Get the tool touched off here. We're going to 0 our cross slide, and I may set a diameter on the DRO. We'll go ahead and make a cut. I usually do 100 thousandths at a time, It's an easy number to keep up with on this lathe because it's 200,000 per revolution. So every rough and pass, just go in 100, depending on what you're doing. If you don't have a lot of cuts to make, it works really well. 10,000 feed rate. If you guys don't remember, this is ductile iron that we are cutting. It's just like cast iron. Watch the dial indicator. Approach the 0 at the 6 o'clock. Disengage, it's that easy. I'm 6/10 away on the DRO. Go ahead and take another 100. And notice I'm running kind of a low speed. That's 380 RPM. You could run a lot faster, but there's really no need. You're gonna sling the chips more all over you if you run it a lot faster than that. Just that easy. Go ahead and take another pass here. $125 to come off. Should be our finished cut. Shooting for 1.62. And we got about 1.621 there on the mic. That's good. We usually take our thread sizes down about 4 to 5 thousandths under your nominal size. We're going to cut a thread relief in that corner there. So we're going to use our Walter Tools MX22 type of insert here. That's a 1/8 wide full radius insert. We'll probably have to kick it at a little bit of an angle to come in here and be able to get all the way in there. And we'll cut a thread relief, the double depth of the thread, about 110 thousandths or so. So anyway, just going to show you what tool we're going to use right here. I love these inserts. They work really well. Round nose, square nose, threading inserts. They got a lot of profiles for that one tool. That's our radius tool we're going to use, and as I said, probably got to put it at an angle, and the reason why is because the way that the insert is ground, you have a little bit of this edge that would actually be crashing into that shoulder. I can't get all the way down in there without starting to rub that insert. So this is why I love a multi-fix tool post so much. Every 9 degrees you can drop it in, so we're just going to rotate it 1 notch, 9 degrees over, Very simple and easy. We can come right in there and use that same exact tool, no problem, and cut that thread relief. Got everything ready to go. Cross slide set to 0, compound set to 0. I'm using compound end feed on this. We're gonna make a scratch pass and go ahead and check it with our screw pitch gauge. And 12 pitch, I can engage that half nut anywhere I want on that dial. And see, with that speed right there, we're running 180 RPM on, and just nice, slow, and controlled. And I can bring this all the way up. I actually messed up there. I forgot that I got to adjust the tool, so I got ahead of myself. I'm going to go ahead and reset this dial indicator to that 0 right there, because the tool is right where we had it before. Okay, that was me moving the tool in the compound. It got out of alignment with that 0 there. No problem. Just a 1 thou scratch pass right there. We're cutting 12 threads per inch. I know you guys probably can't see that, but I'm checking it. Always verify your pitch, and we are cutting 12 threads. So ready to continue on with that guy. This will be the last cut at depth. 62 on the dial. And we're going to come back and just make a spring pass through there, maybe a couple times, just to clean the thread up. Do it one more time. There it is. I'll do some measuring, but that should be right where it needs to be. I'm going to use our radius tool and just clean up that last thread a little bit. We're going to go in with another Edge Technology tool. This is one of their chuck stops with the tallest parallel in the set that they provide. And I've got the center spider here. I've got a few of these that are turned to fit the bore of this chuck. That's all you got to do when you get these. You just got to machine these plastic spiders to fit your chuck through bore. They got magnets on the back here that keeps it sucked to the faceplate of the chuck. Get rid of any chips that might be on there. Just like that. You can leave it in the middle if you want to. You can turn it, whatever. I just kind of like splitting it in the center. And then that's going to give me a stop for the flange of the hardtail nut to kind of push against and keep it from maybe trying to walk back. Let's go on with our steady rest. Give the ways a wipe there. And I've already wiped the bottom of it here to make sure there's no chips. And it's just easier to start with the bottom clamp off, because you got to kind of go down. You go down far enough that the nut just comes off, so I just take that off and then slide it up from the bottom. Like that. Now let's see where we're going to line up at. Like that, so we can bring this forward a little bit. We're going to bump this around to make sure it's running true. All I'm doing now is just kind of holding it in place so we can get our rollers up here kind of close. And if you do this, what I'm doing right here, just make sure the lathe is off. You don't want to reach over a spinning part. So when we make adjustments, we'll be doing it from over here on this right side. That should get us pretty close right there. All right, we'll put the indicator on here and we'll just bump this around true. I'm going to go ahead and snug this a little bit more. Shouldn't need much, but we'll go ahead and get it bumped around. All right, need to go find a little salt blow hammer and we'll get it indicated in. Moving without even bumping it there. I think I need to put a little more torque on the chuck. It's gonna be pretty easy to move. So I think this is gonna be a little trickier than I was hoping it would be, because there's a little bit of paint, like a primer coating on that flange. So it'd probably be better if we polish that off of there. But let's see if we can get it there and if it'll stay. It's just going back and forth. So that's 1, 2. That's pretty close right there. Let's see if we can get the steady rest. I'm going to put it in a low gear here. Oh, first thing we need to do is tighten up our steady down here, the bottom clamp. Go ahead and get it tight. Just touch it like that. Just touch it like that right there. All right, so that's 1.5, it's between 1.5 and 2 thousandths total. What I'd like to do is move this down here to the flange side and see if it's running true. This may be running out, throwing this out a little bit right there. Okay, this side's looking good. It's got 1 thousandths run out, which is perfectly acceptable for a 3-jaw chuck. We're gonna leave it alone, but I am gonna retorque it because I don't have it super tight yet. We'll go ahead and do all 3 pinions, give it kind of the equal torque on them. Looks like a 0.5 thousandths run out right there, so that's going to be good. I think our setup is going to be just fine where it's at. I believe some of what we're seeing is a little bit of out of roundness that was turned into this whenever I machined it. So you have approximately right there where I'm indicating about 1.5 thousandths out of roundness. But we're going to roll with it. We're just going to machine it just like it is. I don't want to take this down any further. You know, typically what you want to do is once you have this set up, try to machine you a true spot. In this case, what you would want to do is come in here and machine you a center, like a 60-degree center, so you could bring a bullnose center or a life center up here to hold it. Turn this OD or skin it, just make you a little undercut true with the center, and then readjust your steady rest. But that little bit that we got right there, that's not going to hurt anything, and it's going to work out just fine. So we're just going to roll with it just like it is. I realized that I should have had it down a little bit further because we're going to part 2 inches of this off. So I just kind of give myself an extra little bit of clearance right there for chips and things like that. And we may need to make a little cover to keep the chips out of the rollers here. But I'm just adjusting that down. So I wanted to point that out so somebody didn't say, well, you moved it down. There's the ring where we were rolling it right there. And we'll come in here and lock our set screws just on the 2 bottom. Leave the top one loose so that you can apply pressure on it as you need to. Sometimes you'll get a little bit of chatter in it. You can put a little bit more pressure on this top finger here and kind of get it to smooth out some. So for our parting, we've got a couple of flavors here to choose from. We have a high-speed steel blade that's custom ground, and we also have carbide insert. All right, typically we use our carbide. It's a little bit more efficient. In this case, I'm going to go with the high-speed steel, and the reason why I like going with tool bits like that sometimes is because this is a sharp tool. The way that I've got that ground, that I've just got a little radius honed on that edge, but the cutting edge is very, very sharp. It's like a knife edge. That's going to produce less tool pressure versus a carbide insert. Most of these inserts are molded, all right, and they're not super sharp to the touch. They have a little bit of a round edge on there for cutting. You know, most of your carbide inserts for turning and milling, they're all that way. Some of them are ground, not all of them. But this being ground is going to provide a little bit more free machining capability here, and it's going to help reduce chatter and vibration in it by having that sharp edge and getting under the material versus a carbide insert that's really trying to push that material away from it while it's cutting. So it's just a personal choice through experience that I'm choosing the high-speed steel tool because I know it's going to work really well for this operation. Hopefully. Hopefully it's going to work well. So, all right, what I'm going to do, that's not a very consistent thickness on that blade. I'm just going to use our good old trusty Starrett hook rule. And sometimes I do it like this. Hook the cutting edge and then eyeball 2 inches right there. Doesn't have to be exact. And there's our parting right there. I'll show you this again. And this light up here, I can't ever tell in the video if it's going to be a good video, if it's going to blow it out. I know that it looks better lit up, but sometimes it really kind of blows out what I'm trying to show you. But I was going to do this again. So just take your hook rule, hook that cutting edge, line up that 2-inch mark with the face. Usually I leave just a little bit, you know, maybe 5 or 10 thousandths there. You can look at that and tell. Thickness of the line is usually around 10 thousandths. And then that's our position. I'm going to slide our trusty mag back indicator back up here, and I'm going to set me a 0 point. so that if I want to, we can move this tool out of the way. Well, where were we? We can come back in here to our 0. That's right where we were, and we come up in our DRO as well, 0 out Z. There we go. All right, let's see if we can get this guy parted off. All right, so we've got it in 130 RPM. That's what I'm gonna run this at. So that's gonna give us a surface speed of about 68 surface feet a minute. Figure that. 0.262 times the diameter of 2 inches times 130 RPM. That gives you 68.12 surface feet per minute. We'll give that a try. If we have any kind of chattering issues, we can slow that down and that'll help there as well. So let's go for it. Trying to chatter right off the bat. That's what I was talking about right there. So we're just going to slow it down. Let's just go down to a slower speed. I'm going to put a little more pressure on the top finger here. And the other important thing to try to do is get underneath the chatter. So I'm going to feed it in there a little harder. It's still trying to chatter. Let me go down another speed here. We'll go down to 2. This is going to be 50 RPM. Try to get underneath the chatter. Feeding this by hand, by the way. This is where you're feeling the machine. You're feeling the tool. You're letting it talk to you and tell you what it likes or what it doesn't like. I'm going to go ahead and kick it back up another speed. Now we're getting to a smaller diameter there. You can hear that chatter trying to come back in, but I'm just trying to keep the tool underneath it. I'm going to do something else here too. Usually cast iron and ductile, you really don't need to worry about lubing it, but it does help sometimes. I'm going to go in with just a little bit of the anchor lube here to try to help those chips. Just helping to get those chips out of there. Cutting through into the thread now. There it is. I'm going to keep going and just cut that last little bit of thread there. All right, there we go. Next up, we'll just get this side faced, get cleaned up, and then we'll bore it out. Yeah, you can see it usually goes at a little bit of an angle as it's parting it off. That's what, I'm sorry. We'll just take 10 thousandths here. Okay, that should do it there. Now I'm going to set up a boring bar and we'll go start boring it out to our bore size required for 1 5/8 12. I'll get that figured out and let you know. Okay, let's figure out what our bore size is going to be for our thread. This is a formula that I learned a long time ago that I've used many times, especially for a lot of the hydraulic parts that I machined over the years. A lot of your hydraulic cylinder components, the pieces that go together. They usually use a 12 pitch thread for most of that stuff. And that's typically anything over, say, 1 1/8 inch, usually is just a 12 pitch thread. And that's just kind of like a standardized system across hydraulics. And it works really well. Most of your lathes easily cut a 12 pitch thread, you know, engaging a half nut anywhere you want. It's just a really good thread that works for a lot of stuff. So that's why I'm using a 12 pitch, because it really does work well. All right, so to figure out your bore size, this is what you do. All right, you're gonna take 13 thousandths, so we're gonna go 0.013. You're gonna multiply that by the thread percentage that you want. The most common is 75%. That's usually what all of your tap drill sizes are figured out to. You know, if you got to drill a hole and run a tap in there, you're usually figuring 75%. So 13 thousandths times 75, and you want to divide that by your threads per inch. We're cutting 12, so divide by 12. And that leaves you 81 thousandths. Let's just round down 81 thousandths, okay? Remember that number, 81. What's our size here? 1.625, nominal 1 5/8 minus 0.081 equals 1.544. That's the diameter that we want to bore that to. This is also the diameter that if you were drilling a hole is what you would be shooting for, or whatever your closest drill size is if you don't have something that's exactly that right there. You can go down to 70%, some cases 65%, but 75 is the general rule of thumb that most people use, I believe, in manufacturing is 75%. So anyway, one more time, 0.013 times 75% divided by 12, that's the threads per inch, equals 81. 1.625 is our diameter minus 0.081 equals 1.544. So let's go get our workpiece bored to that size right there. All right, we've got a bar set up, we're ready to cut. I was just going to show you if I hook that thread again, it's just over 1 inch back there. So really all we got to do, I think it's just going to end up being a through bore. I don't know if the inside of that is going to be larger than our 1 5/8 size, but we'll find out. Let's go ahead and get a cut and start getting it cut out of there. It's going to be 100 thousandths, see if it'll handle it. Just make sure the steady rest is supported good. Yeah, that's working great. Well, let's see where we're at now on our diameter. About 162. All right, yeah, so we got a little ways to go. What, about 400 thou or so? I feel pretty confident that we're going to end up cutting into this other bore behind the threads there. So we're going to go ahead and make a stop before we go any further. So I'm just going to go ahead and I'm going to touch the face with our tool, zero out our DRO, and I'm going to go to a negative. Let's go 1.25 inches. So our thread length, again, our thread length is 1 inch long. So as long as we bore in there 1.25 inches with a thread relief, we should be just fine. So I'm going to go a negative 1.25 on our Z, 1.25 inches, and that should work good right there. Come back to where we were at, should be right there. Take another 100 thou. And then so this time we're going to be watching our DRO. We'll just pull you back. Watching our Z. See if we clear it. Right about here. Just touching that ID. Yep. That's working out pretty good right there. I'm going to go ahead and get another measurement. This bar has got a little bit of magnetism in it. That's why those chips are stuck to it. I need to fix that one day. Let's see where we're at. 1.460. Y'all remember where we were taking it to? Well, I wrote it down. 1.544 is what we want. So we're getting pretty close, within about 100 thousandths, right? A little, well, under 100 thousandths. So we'll just take about half of it now. All right, one more pass and we should have that where we want it. I'll get a telescope gauge and a mic and we'll measure it. All right, we got our telescoping gauge and 1 to 2 micrometer. Measure this a couple times and see where we're at. .510, a little under that, about a half a thou, 509.5. I'm just going to call it 510. This is not a super precision board that it has to be on. We're just shooting for 75% thread engagement. So same thing. Let's just call it 1.510. So it'd be 20, 30, 40. That's 30 thousandths plus another 4. So 34 thousandths is what we need to take out. I'm just going to go ahead and dial that in. 10, 20, 30, and 4. All right, let's make that finish cut. All right, let's see if we hit our target. 1 inch 544 was the number that we were shooting for. Let's see what we got. Looks like we got 545. Just over a thou over. Perfectly fine. I'm good with that. All right. So what we need to do, we'll go ahead and cut a chamfer on that. And I am going to machine a thread relief in there as well. Something that I like doing. I think I got a solid carbide bar that I can reach in there that has a nice radius on it that we can machine a thread relief. I'm going to look at my Micro 100 tool bits and see what we got to do the undercut, thread relief, and the thread itself. But for our chamfer, we can just go ahead and set up this guy, the old Armstrong tool, flip it around here in this orientation, and do it like that right there. Got a nice chamfer there. Start the thread, and let's just barely break this outside edge off of it. I'm doing that so I can see it. Just like that. Just want to break the outside edge. Okay, I found the tooling we're going to use for our thread relief and our internal threading there. So these are some of the Micro 100 tools for their tool that's considered the Micro Quick. So you have these adapters here. These are great tools for CNC lathes, by the way. the way that these are designed, but of course you can use them in manual machines. They have a lot of different size tools, and they have them in different shank sizes too. So this particular one is for 1/2 inch. So this one right here, the QFR, this is going to be your full radius, full inside radius right there. Just a beautiful grind and polish that they put on that carbide. And so this one is the 1.5 inch. So you got a 1.5 inch reach inside there. So that's going to work for our thread relief. And then this is the QIT. So quick internal threads. It's also 1.5 inch. So that'll cover the threads, since we're going to go 1.25 inches deep in there. And the way that these work, you see that you have an angle ground on the back, and you have a relief ground right there. So the back is what aligns the tool to keep it center, square. The top is where the set screw tightens in there. That is going to, force it back and keep it tight into the holder. So you have a set screw there, and on the side you can see where the pin is actually pressed in there. That's the pin that aligns this angle here on the tool. So it doesn't matter which tool you stick in here, whenever you push it back, it's going to naturally push against that pin and center up there, and then you just lock it in. So that's a really nice system. When you're done with one, you can simply pull that out. If you need to change it out anyway, you can stick it in there. And there's no having to, tilt it one way or the other, get it centered up. All you got to do is adjust your height to make sure you're on center. And then, so once you put the tool in there, you just simply snug that set screw there. It's going to push it back against the pin. It's going to be nice and square, just like it should be, and you're ready to go to town. So we'll go over to the lathe and start getting this finished up. Okay, I've already got our tool ready to go. I touched the face, so we've got a depth set at 1.25, and I took the tool inside and just barely touched the ID, just like you would when you're threading. And I set our diameter on the DRO. So once we start cutting, I got to simply just look up at the DRO, and we'll take it out to about 1.630 and 1.635, somewhere there, and that should be a good diameter for our thread relief. All right, that did great. We ran it nice and slow to try to eliminate any of that chatter. I'm actually running 50 RPM right there. So we'll go ahead and take this tool out, and we'll put our threading tool in there. We've got our threading tool touched off. It's ready to go. I've got our depth set to whenever it comes to the center of that thread relief back there. I've got a 0 on the DRO. You can hear there, and then we have this 0 set up on the dial indicator. So 0, 0, and I have a 0 on the cross slide for the touch off of the tool there. And what we're going to do is make our passes through there, get it really close, and then we'll start hand fitting it with the actual nut. This guy right there, we'll just hand fit it until this screws together the way it's supposed to. We'll make our scratch pass through there, make sure everything's lining up good, check our pitch, and then we'll try to get you a close-up of the thread. All right, so you have a couple things happening here. You have an audible stop of the cut where it goes into that thread relief. I'm looking down here, and now I'm on 0, so we should be nice and clear. Back the tool out one turn. Bring it back into my 0. Easy as that. In case you're wondering, I'm running mid-range here. We're running 130 RPM. We're going to try that. I'm hoping that the chatter is going to stay out of there. If it starts chattering, we'll slow it down a little bit. All right, so this is where I'm going to come in here and just check it with our screw pitch gauge. And we're good. We're cutting 12 threads per inch, so we can carry on and get this guy threaded. All right, we're sneaking up on our diameter. I want to go ahead and do a quick test fit. I don't think it's going to go, but that's usually what we do is, yeah. All right, so I've got probably a good 10,000 still to come out of that. All right, I took 2 more light passes through there. Let's try our fit now. I've gone exactly 62 thousandths on the compound, which is the actual number theoretically that you should take if you're cutting a 12 pitch thread with the compound set at 30 degrees. There we have it. I went gently with that. I'm trying not to jam it if there's a chip or something and everything's dry. I probably could have backed off a couple of thousandths. I felt pretty good about taking those last 2 passes. We got a good fit. There's nothing wrong with this fit whatsoever. This is going to be captured together. What I'm going to do is go ahead and get this ID polished up nicely. Get rid of these burrs, and then we'll go ahead and probably just go ahead and Loctite this guy together right here on the lathe, so we can get the lathe work finished up before we take this out of the machine. Okay, we're going to use our Loctite 680 retaining compound. I'm going to put some in there, Got a little acid brush here, but we'll slick it around, make sure all the threads are covered. Same thing, put a little bit on the male threads here and use the brush and make sure that they're evenly distributed, or the Loctite is evenly distributed. All right, that's looking good inside there. So now we'll go ahead and put a little bit on our threads here as well. .680 is the retaining compound that we always use, Dad and I, for a lot of different jobs. Jobs where you had sleeves, you know, that you could put into a housing that didn't actually require a, you know, interference fit. Get it off the face there. Okay, here we go. Now what I'm going to do, I'm not going to wrench this in there hard. I'm going to just, we're just going to get it going just like that. And I'm going to turn the lathe on and hold it and just let it kind of, you know, lock up face to face there together. Just like that, right there. That should be good. We're gonna, it's getting close to the end of the day here, and so I'm just gonna let this sit overnight. I got some other things to work on. I'm gonna go do some other stuff. We'll let this set up, and then when I come in the morning, it'll be ready to go. We'll go ahead and finish turning this OD here, and then that'll be it for the lathe work. After that, we'll go to the mill to put our pin in there. All right, guys, it is the next day. Our Loctite should be well bonded by now, and we're gonna go ahead and get this turned down. So when I turn this is 2 1/4 diameter. I'm gonna go ahead and measure this area here, because this is what we're wanting to match up as close as we can. All right, it looks like that's going to be 5, 6, 7, about 8 thousandths under 2 inches right there. I think I did that for clearance to slip through the back of the hardtail casting. All right, so let's go for it. We're going to try it with just a steady rest for now and see how it reacts. If we're starting getting some chatter, what I'll do is I'll put a center here, but we probably have to tool a 60-degree center, just enough so that a live center can support that. But let's try it without it first and see how the machine reacts, if it's actually going to work here. We'll just take 100 thousandths at a time. Working just fine. Get a measurement, see where we're at. We'll just split this into 2 passes. Should be just over 50 thousandths. All right, so that's 2 inch, 50 exactly. And this was measuring, I believe, 7 under. Measure it again real quick. 7 under, so we got 57. So we'll just split that in 2 passes and finish this up. So I just went for the same diameter that I was measuring this guy right here. And remember, we had about 1.5 thou run out here whenever we first indicated it. And you can see that right there. And it's not going to be a problem. As long as it's under 2 inches, it'll fit through that bore hole. Let's see if we hit our target right there. I was trying to hit 7 under, and it's 7 under right there. So it's measuring the same. You just got about 1.5 thousandths difference there out. So nothing wrong with that. That's good to go. All right, guys, that is finishing up the lathe work that we have planned for the hardtail nut today. I'm really happy with the outcome. I think this looks really good. We hit this with some fine emery just to kind of polish that up, and it looks really good. This is exactly how I was envisioning modifying the stock hardtail nut to adapt the threads that I wanted to put in there, and I think this is a solid repair right here, or solid modification. And I think because of the length of the video today, I wasn't planning on it being this long, but I think we got about an hour-long video now. Let's just stop this here. The next video, we're going to come back. We're going to set this up in the mill. We're going to go ahead and get it drilled and reamed for a pin. I believe what I'd like to do is go ahead and use a tapered pin. We'll get this set up. We will get our hole drilled and reamed in there for our tapered pin, get this installed. We'll probably end up coming back to the lathe here so that we can do a nice turn finish on that pin and make that kind of match our 2-inch diameter. And then once we do that, we'll go ahead and get all this put back together. We'll install this in the hardtail. We'll get the hardtail mounted on to the main vise. You guys will see the new handle that we made, the spindle, and everything together in its entirety on the next video. All right, so I hope you guys enjoyed the work that we performed today, and I hope to see you back here on the next video where we finish up the USA made hardtail vise.